Welcome to Lecture 18, Alternating Series. So as an overview, most of the series we've seen so far have only had positive terms, and actually some of our, well, there should be tests, some of our tests required this. So what about this series? Here, where this is the harmonic series, except the terms alternate positive and negative. So we can try to use some of our prior tests. Let's see, which one should we start first? The divergence test does not help. Divergence test. This does not give any information because the terms go to 0. So what about the ratio test? So here, the limit of the absolute value, we could just ignore the negative terms. So the limit of an plus 1 over an, that limit is going to be n plus 1 over n, and that's going to be 1, so no information. So we really don't have anything to tell if this diverges or converges. Let me start with the definition of an alternating series. An alternating series is of the following form. So I should probably clarify that Bn is assumed to be non-negative. We don't want the Bn's to be alternating in sign as well, otherwise these could all end up being positive. So an alternating series is any old series that alternates in sign, like this one up here. And while I'm at fixing things, let me add s back to that test. Okay, so the alternating series test is, suppose we have a, I forgot my Bn in here. So suppose we have an alternating series where the Bn's are all now strictly positive. Then the series converges if these two conditions hold. If the Bn's tend to 0, and if they are, this just says they are decreasing. So actually, I shouldn't say they're decreasing because several of these could be the same. So let me say better, non-increasing. So sometimes we can write these two things and we can summarize it, and we could just say Bn decreases to 0. That's the shortest way to write both of these. So if we have an alternating series and the Bn's decrease to 0, then the series converges. No ifs, ands, or buts. This is not the case of positive series. Remember, for positive series, just because the terms tended to 0 did not mean it converges. Here, it does, assuming that they actually are decreasing. We don't have anything bouncing up and down. Okay, so here's the alternating test again. Again, let me do some examples. I've got to fix that error. That's a Bn, and I'm going to summarize this as saying Bn decreases to 0. So here we can apply the alternating series for this test. Notice that indeed these terms decrease to 0, and they decrease to 0 because 1 over n plus 1 is less than or equal to 1 over n for all n. And I should say, let me clarify what I said up here. I said the Bn's are decreasing to 0. This, as we've seen before, this is not necessarily for all n, but this is for some index, for some capital N, this holds. So we don't care if the first 2 terms or the first 10 terms bounce around up and down, as long as eventually the terms are decreasing. That for some index, this holds. Next we have what's called the remainder theorem. So if S, big S, is the sum of a convergent series, convergent alternating series, so once again, I'm assuming, if I don't say otherwise, that this Bn is non-negative. And the remainder is the difference of the sum and the partial sum. So I should probably say the nth remainder. So the partial sum is the first sum of the first n terms, and the remainder is the sum of the everything else, so the whole tail. And so this says that that remainder can be no bigger than an absolute value than the very next term. So this tells us that alternating series converge pretty darn quickly. So I think this is best seen by doing an example. So here's our alternating harmonic series. This is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus or minus, etc. So let's say I'm going to do the first 4 terms, otherwise I'm going to have to add up too many fractions. So let's call this, so this is the fourth partial sum. This guy here is equal to B5. So S4 is, what is this? This is 1, so else, 12th. This is 12 12s minus 6 12s. That says plus 3. So this is 7 12s, I think. So what this says, by the remainder theorem, this says that S minus, so whatever the heck this sum equals, remember this is what we would like to know. What does that converge to? So we don't know, but we know that S minus 7 12ths is less than or equal to, well, actually let me remind you that that is by definition equal to R4. This is the fourth remainder or error term. And that is no bigger than B5, which is 1/5. So in other words, when I say B5 is, no, when I say the absolute value of the remainder is less than 1/5, that means that the remainder, which is S minus 7 12ths, is between negative 1/5 and 1/5. So from here we can add 7 12ths to all three sides of this equation, and we get 7 12ths minus 1/5 is less than or equal to S is less than or equal to 7 12ths plus 1/5. So this, let's see what this is. This is that is 35/60ths plus 12/60ths, right? Okay, so, and of course the left-hand side is 35/60ths minus 12/60ths. So this tells us that the left-hand side is 23/60ths, less than or equal to S, is less than or equal to 47/60ths. It's 47/60. And that tells us that S is, let me go into on my laptop, which is right in front of me, into Wolfram Alpha, and S is between, that's negative 0.383 and 0.783. So we don't know what S is, but by just looking at the first 5 terms of this series, we're able to conclude that S is between these two numbers. So we're able to narrow this down quite quickly, and that's the main point of remainder theorem, is that it allows us to estimate the sum really quickly. If we had done 10 terms, we would get a much closer approximation, and you get exactly the. You know the precision too. If you want to estimate this to 1/10 accuracy, we'll go out to the first, in this case, 10 terms, because the 10th term is 1/10. If you want to estimate this to 0.01 accuracy, go out to the first 100 terms, because that's B100 is equal to 100th. Okay, so next, let's recall the harmonic series that we've seen. The harmonic series has this, so so that's the series 1 over n equals 1. So this series diverges, but if we make it alternating, it converges. So that leads to the following definition. A series of this form is called absolutely convergent if, when you make all of the terms positive, it still converges. And it's conditionally convergent if the series itself is convergent, but it's not absolutely convergent. So for example, if we make this series, so consider this series, this is a series is convergent, but if we take the absolute value of that, then this goes away, and it is no longer convergent. So this thing here is conditionally convergent. So two examples. Well, this first one is similar to what we. Well, let's go over both of these. So this one here is almost what I just put up on the screen. So that this is the one we've seen in the previous slide. Minus 1/4. And notice that this series, take the absolute value, is the harmonic series. So this one converges, this one diverges, and so therefore this series by definition is conditionally convergent. Now compare that to this series, this next one below. So here we have an alternating series, but it's 1 over 1 minus 1 over 2 squared plus 1 over 3 squared minus 1 over, oh, I'm sorry, not squared, cubed. I can make those into cube, 4 cubed, plus or minus, so forth. So this thing here, this converges. You can do the alternating series test. These terms are decreasing in magnitude, in absolute value, and it's an alternating series, so it automatically converges. And notice that if I take the series, if I take this series, then I get 1 plus 1 over 2 cubed plus 1 over 3 cubed. Well, actually, why don't I just write this as, 1 over n cubed, and this converges. It's a p series with p equal to 3. So while this was a conditionally convergent series, the fact that both of these converge tells me that, where do I want to write this? This one here is absolutely convergent. So in both of these cases, you might be thinking now what's coming next is that it's harder to make a series. Well, if the absolute value of a series, I guess the series of the absolute value of the terms like this converges, then it's not hard to fathom that the regular old alternating series is going to converge as well. And that is in fact the next result. A series is, if a series is absolutely convergent, then it is convergent. So this basically is saying that if this converges, then the series converges. Another way to state this, if A, then B, you can state this as if not B, then not A. So a logically equivalent way to state this is if a series diverges, then we know automatically that I don't have a name for this. absolute values. I don't want to say absolute value of the series because that would imply that, but I'll just say then this series also diverges. Okay. Okay, so in the last slide, I'm going to show you something that is truly remarkable. This is going to blow your mind. If we have a series that is convergent, but not absolutely convergent, so I don't know why I didn't just call this conditionally convergent. It means the same thing. So really, I mean, AN converges, but the absolute value of the ANs, these diverge. Then for any number alpha, alpha can be pi, it could be 0, it could be negative 100, it could be infinity. There is a way to rearrange this series to make it converge to anything you want to your favorite number. Doesn't seem like it should be true because we all know a plus b equals b plus a. Order doesn't matter. But when we're talking about infinite things, order matters. So for the most basic example of a conditionally convergent series is the alternating harmonic series. So I will use that. So let me consider, do as an example. So let me take a series, AN, and let me do, so 1 minus 1/2. So here's the alternating harmonic series. Minus 1/6 plus 1/7 minus 1/8 plus or minus. Okay, so actually I'm going to erase that and I'm going to say, I'm going to do one more term, plus 1/9 minus 1/10 plus or minus, etc. Okay, so now notice that these first three terms add up to 5/6. And now, what do I want to? Oh, I know what I want to do. So I want to I don't want to rearrange. I want to write the remainder of the series as minus 1/4 minus 1/5 minus 1/6 minus 1/7 minus 1/8 minus 1/9, etc. So now, notice each of these terms here is greater than 0. 1/4 is bigger than 1/5. 1/6, oh, I just accidentally erased that. Let me try that again. So 1/4 is bigger than 1/5. 1/6 is bigger than 1/7. So this is positive, this is positive, and so forth. So what we have is we have 5/6 minus something positive, minus something positive, minus something positive. At the end of the day, this thing has to be strictly less than 5/6. Oh, that's not a 6. Has to be strictly less than 5/6. Right? Obviously, 5/6 minus a bunch of positive things. Okay, so now I'm going to rearrange this series. I'm going to write this series as. So what I'm going to do is so here I did plus, minus, plus, minus, plus, minus, plus, minus. I'm going to write this series, I'm going to write the first two positive terms and then a negative term. Then the next two positive terms and a negative term, and so on. So this series I'm going to write as minus 1 plus 1/3 minus 1/2. So the next two positive terms are plus 1/5 plus 1/7 minus 1/4 plus 1/9 plus 1/11 minus 1/6. So you see what I'm doing? I'm adding up 2 positive, 1 negative, 2 positive, 1 negative, 2 positive, 1 negative, etc. So plus, minus, etc. So, okay, so now what do I have to do here? So Okay, once again, I have this is equal to 5/6. And now let me group these three terms. I'm going to group the terms together in triples. And what you will notice is that 1/5 plus 1/7 is greater than 1/4. That's, you can check, this is 7/35 and 5. This is 12/35. And 1/9 plus 1/11 is going to be bigger than 1/6. So, so this here is going to be positive. This here is going to be positive, and each one of these triples is going to be positive. So now we have 5. Again, I did that. I wrote 5. I'll just make that into 5. So here, this sum is 5/6 plus something positive, plus something positive, plus something positive. So whatever we get clearly has to be bigger than 5/6. Weird, right? So I took a series that equals, well, and I'll just tell you particularly that this thing is actually converges to the natural log of 2, which is 0.692 if my memory serves. But, well, that's definitely less than 5/6. So we have a series that is, whatever it is less than 5/6. But if I rearrange the terms, I get something greater than 5/6. What the heck is going on? So here's what's happening. How do I want to write this? So this series has a whole bunch. So okay, here's what I'm going to do. I'm going to take that original series, and I'm going to group together the positive and the negative terms. So here are the positive terms. 1, 1/2. Oh no, it's that's not right. That should be 1/3, 1/3, 1/5, 1/7, 1/9, 1/11, 1/13. So here are the positive terms, and then let me write down the negative terms. -1/2, -1/4, -1/6, -1/8, -1/10, -1/12, etc. So it's I'm not going to prove this rigorously, but I'm just going to outline how a proof would go. If you're interested, take real analysis, Math 453 or 454, depending on it's either at the end of one or the beginning of the other course. So, okay, so here's what's going to happen. If a series is conditionally convergent, in other words, if this diverges, but this thing converges, then the only way that can happen is if this sum, if the sum of these is positive infinity, and the sum of these is negative infinity. In other words, what we can do is let's take our favorite number. Let's say that our favorite number is pi. Let me draw a number line here. So we're going to start at 0, and let's say pi is up here. So starting at 0, I'm going to take, so I have two buckets. I have a positive bucket and I have a negative bucket. So I'm going to start drawing from my positive bucket, and I'm going to keep adding numbers together. I'm highly exaggerating. I'm going to need a lot more than just a couple terms to get all the way up to pi, but I'm going to keep adding these things together until I jump over pi. Okay? Now I'm going to go to my negative bucket, and I'm going to grab terms, and I'm going to keep adding negative terms until I get back on the other side of pi. Now I'm going to go back to my positive bucket, and I'm going to keep adding. So every time I add a term up, I throw it away. So I take my remaining terms, and I keep adding terms up until I get on the other side of pi, and I can repeat the process. Now I take negative numbers, and I add those, and eventually what I get is, well, if suppose I zoom in a lot. So what I have is I have a jump here, then I have a jump here, and then I have a jump there, and so forth. And what I keep doing is I keep converging upon pi, and I have created a rearrangement of my series to equal pi. And you can do this for any old number you want. And that should strike you as really weird. Once you see how it's done, it's not quite so weird, but just the fact that you can take an infinite series of numbers and you can rearrange it to equal anything you want to. Well, not always, but anytime it's conditionally convergent. That's pretty remarkable.